Okay, sweet. So we're just gonna get started with day 28. I think I'll probably be only able to complete Anki tonight. It's been about a week since I streamed last, and so we have a bit of a pile up. Um, I would like to. I guess I'm at pretty much two. Lol. Okay. One thing that I was kind of struck by recently, I watched this podcast with I guess this is the Andrew Huberman, but I was actually think one that I'd watched before. It was like a science of learning and stuff, but it caused me to realize like how important testing is. And yes, it's the case that like I test with Anki, but it just like sort of reinvigorated me with just the notion of testing, not only for testing after the fact when you're using something like Anki, but also in that when you're working with something, you ought to be in generating hypotheses about how this thing is or what this thing is, even before you aren't like you couldn't reasonably have a great idea about it, just so you can like generate the generate it and test it and be proven wrong, because that's great for memory. Not only because it's that feedback for the thing you just learned, but also because generating that hypothesis is a form of cognitive load. That cognitive effort is helpful for retaining retaining knowledge over material, pushing off forgetting. So, yeah. We'll see how things go. Another thing is for like mental effort. So cognitive load is important for sort of generating an idea. And so I'm thinking I might find some ways to spend more effort in doing some of this stuff. Because maybe like I derive a particular something, right, from a different form. So I just have it just ingrained, Yeah. We'll see. I think I'd just like to finish the test first. Slowly but surely chipping away 1 hour at a time. And then I guess we'll see where we're at from there. So. Okay, inflection points. So first you identify, so you take the first derivative and find the points at which it evaluates to 0. Yes. And then from that, you take the second derivative of those points, or take the second derivative and plug in those points. And at that given point, you can find the minimum and the maximum. Okay. Yep. Okay. So. Okay. Inflection points aren't about minimum or maximums. I had the wrong thought there. What does applying the squeeze theorem look like in the context of working with a function that has a component that is bounded? So for the component that's bounded, you take the upper and lower bound, and then you, I feel like you multiply the upper and lower bound. Oh, so you guys guess you have like a complex function or a function where a component of it is bounded. I guess that's clear. And then you take the upper and lower bound of that component and then substitute it. So you'd have like the original one, it's greater than lesser than the upper bound is less than or greater than the lower bound. And so you take the upper bound and have it in the upper area and lower bound have it in the lower area, evaluate them for their limits. And if the limits are equal at the given value you're trying to evaluate, then you know that via the squeeze function that the original function has the same limit. Two constants multiplying by a term that approaches 0. Yep. Showing both results are bound in the same limit. Perfect. The derivative of tan of x. I think this is like secant squared x. Okay. Secant squared x. Okay. Where cosine is not equal to 0. Okay. Okay, so I'll just have to remember where cosine is not equal to 0. This formula, this is the two-angle thing. Two-angle formula. Yeah, double angle. We'll just redo that one. Double angle formula is where 2 times sine, or sorry, a sine of 2 theta is the same as 2 times cosine times sine. Okay. A Pythagorean identity are derivatives of the Pythagorean theorem. The main one is let's see. So this would be. Oh, okay. Okay. So this would be cosine squared theta times sine squared theta equals 1, I believe. Because if we go back to the unit circle, before I evaluate, I'm going to spend more effort to justify. So if we go back to the unit circle, and we have the radius of the circle being 1, the cosine is adjacent over hypotenuse. And if the hypotenuse is 1, then it's the adjacent. And then you have the cosine, the sine, which is the opposite. And so it would be 1 equals cosine squared theta times sine squared theta. I don't know though. That's probably not even clear at all. Yeah, we'll just do that. Okay, so I'm right. That was correct. As is derived from the unit circle. Hell yeah. Nice. Actually, I'm psyched about that. Okay. Okay, this is the Pythagorean identity. What is the cotangent cosecant Pythagorean identity? So it's 1 plus a cotangent squared theta equals cosecant. The power rule for derivatives in calculus. This is when you have. This is how you take derivatives of components of a function that have exponentials. So you take the given. Oh, let's see. Okay, so yeah. So if we have x to the 4, what we do is bring the 4 down and do 4x, and then decrement the exponent by 1. So it'd be x to the 4. The derivative of x to the 4 is 4x to the 3. Perfect. This is the tangent secant Pythagorean identity. The antiderivative of sine. So I believe this is tangent. Cosine. Womp womp. Okay. This function is 1 over. This would be the inverse of cosine, which is secant. Yep. The sine is opposite over hypotenuse, or that would be y in the unit circle. Tangent quotient identity. Oh, okay. So this is This would be sine over cosine. And the reason why that's the case is because we'll just exert some mental effort here. So I know that the tangent is equal to the opposite over adjacent, tan OA. And I know that sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. And so when we divide this, what we can do is just flip this guy upside down. And then these cancel out. And then you're left with this right here, which is opposite over adjacent, which is bada bing, bada boom, arctangent. Okay. Okay, this is the tangent quotient identity. How do you apply L'Hopital's rule for finding a limit of rational functions in calculus? I believe it's the case that if you're trying to find the limit, but you can't, or it's undefined, or not undefined. Yeah, I guess undefined. If it evaluates 0 over 0 or infinity over infinity, what you then do is you take the derivative of each component and then try to reevaluate the limit. In indeterminate form, differentiate the numerator and the denominator separately. Take the limit of the new fraction. Okay. So I guess that is interesting that for L'Hopital's rule, we can, like, that actually works, you know? If we differentiate, like, regardless to how many times we differentiate for this given case where we have a rational function, it's still, the limit remains the same. Let's see. Let's think about that. Okay, So if we differentiate, so let's just think about that real quick. So if we have the limit going here, and then we just kind of do this business, and then we have this one go zooey, and then we have a nice little dotted green line here. Oh, actually, we'll make that solid. Okay. So, if we take the derivative of this, we're going to see it be pretty much 0, and then it'll quickly approach 1, and then it's going to approach infinity quickly. And so if I continue to take the derivative of this, yeah, it seems that yeah. So it seems like I would just, yeah, it would just continue to get the same thing. But this is actually not exactly applicable, because, yeah, I don't know why I actually came up with this. Because this is a, well, I guess this is one case. Yeah, maybe we'll look up, like, the reasoning behind L'Hopital's rule, and why it's the case. It makes sense in, like, that form, but I guess I don't even have a limit there if I'm going to take it at the asymptote. So we will, what is it, like, things I'd like to read, things I'd like to, lessons learned. Aha. Okay, so I want to dive deeper into L'Hopital's rule. L'Hopital's rule. Okay. Okay. Opposite, this is sine. Secant, it is the hypotenuse over adjacent. This is the cotangent quotient identity. Cosecant is hypotenuse over opposite, or 1 over x in the, 1 over y in the unit circle. Gulp. When are you not able to use the power rule? This is when you don't have an exponential like function, or like the term doesn't have an exponent. Yeah, I guess probably exponential function. So if I have like a rational function that doesn't have any exponents, or just any function that doesn't have any exponents, when the function isn't a power of x, okay. The function isn't a power of x. I think that's probably a better way to put it. So I'm gonna have that, send that one through. Inflection points is when these are merely points when the slope passes 1 or 0. Or sorry, when the slope changes from negative to positive, or passes 0. And you find this by taking the second order derivative and evaluating for points where it equals 0. Or sorry, you input 0 and get those points, and those are the inflection points. Set f of x, yep, and see where it's undefined. Perfect. Oh, undefined. Interesting. I guess I would not have expected it to. Huh. We're gonna dive into this a little bit more. I thought I had a intuition for this, but I guess not. What is this? It's 0 or undefined. Okay, 0. Well, I'm going to adjust this. Find where the second zero. Okay, I guess the one that caught me off guard is the undefined. So, let's see. Why is it the case that we'd also look for the undefined ones? Question mark. Could you give me an example of this? Okay, undefined in addition because inflection points is where concavity, the function changes, and this changes can occur. Oh, okay. Okay, that makes sense. Okay, so the reason being is that if we have like the classic asymptote of this guy, like this, that's pretty bad. Oh, that's not it. This is maybe, I don't know, guess depending on how you look at it, concave, and this would be convex. In math, so I guess this is my guess. This is concave and this is convex, but it depends on your perspective. But I'm sure they have concave and convex defined mathematically, And so I'm going to make that guess. Mathematically, how are concave and convex defined? Is concave the frowny face and convex the smiley face? Concave up, concave down. Whoa. Okay, concave. Yep. So it looks like you can specify concave up and concave down. Interesting. So it looks like it's actually, they just say concave up and concave down for functions, and convex is actually more informal. Or I guess in pure mathematics it's used to describe something that's concave up, which was what I think that's what, oh, let's see. I wish I'd written it down or something. I can't recall which one I said for which. Convex, concave, concave, convex. I think I said concave and convex. And I guess it is the case that I did write it down, Lamau. Concave down. And so convex. Let's see. It's concave the frowny face and convex the smiley face. So convex is used to describe concave up. Okay. Yes, so I did have that right, though they just describe it as concave down and concave up instead of... okay. The derivative of tangent of x. The derivative, this is a secant squared plus, the secant squared of x, where the cosine is not equal to 0. This formula is sine, this is the double angle formula for sine. The antiderivative of a sine of x, I think, is cosine of x. The derivative of cosine of x is, wait, is the negative cosine of x. Or sorry, negative sine of x. I had that like a moment ago. This is a cosine. Derivative of sine of x. I'm not sure. Oh, it's just cosine. Okay, this identity cosecant theta is equal to, this is the cosecant, well, let's see. Oh, just the cosecant. Reciprocal identity. Okay. A cotangent quotient identity. This is adjacent over opposite. So that would be sine over cosine. Cosine over sine. Cotangent. Oh, okay. No, that's right. Yeah, I said that wrong. Because cotangent is adjacent over opposite. Okay, secant. This is the secant reciprocal identity. That is cosine over sine. Oh, this is the reciprocal identity, not the quotient one. The cosecant reciprocal identity. This is 1 over sine. The result of taking the left and right hand limits in a positive and negative infinity for a given function does... If the result of taking the left and right hand limits for a given... for positive and negative infinity for a given function, does the limit... If the result... Oh, results in positive and negative infinity. It does not exist at that point, because the limits have to equal each other for when taken from the other angles, or each side. Okay, the function cosine over sine, or adjacent over, this is the cotangent. This is the cosecant. Opposite over adjacent. Cotangent. Adjacent over opposite, or that would be cosine over sine, or x over y. Sine over cosine. This is the tangent. Cosecant. What is the definition of cosecant? The cosecant trigonometric function. This is the reciprocal of sine, and so this would be 1 over sine. The secant reciprocal identity. This would be the opposite of cosine, or it should be 1 over cosine. The definition of cosine is adjacent over hypotenuse. This is the cotangent of theta. Sorry, this is the cotangent reciprocal identity. The antiderivative of cosine of x. Was this negative sine? Ah, shit. Okay, I'm going to have to do a little bit more to get these. We apply the squeeze theorem in either in contrived scenarios where you have 3 functions that are like chained together by like less than or greater than stuff, or if you have a component of the function that is bounded, and presently you can't evaluate the limit, and so you take the upper and lower bound of that and split it out into 2 different functions, and then if the limit of those functions evaluates to the same number, then you know the limit of the function that you are having a difficult time evaluating is also the same. Okay, if you're not able to use the power rule when the when the function is not an exponent of x. This is a expression with 1 or more terms. This is a function wherein I guess the resulting y's are bounded within some domain. Or sorry, some. I thought that would be the range. Is bounded on domain D if there exists finite numbers m and large M such that a domain D for all. Oh, okay. So I guess we're talking about. Okay. Okay, yeah. So we're talking about the resulting. Okay, so so X is a member of this domain, and then the M's are the description of the range. Okay, L'Hopital's rule when we have an indeterminate form, which is 0 over 0, or infinity over infinity. Undefined expressions and indeterminate forms. Undefined expressions are when you have 1 over 0, or sorry, something over 0. Or I believe that's the only case. There may be other cases. Indeterminate forms are when you have 0 over 0 or infinity over infinity. Yep. Okay. Non-existence. Perfect. If you find the vertical asymptote, or how do you find a vertical asymptote for non-rational functions? for non-rational functions. Oh. So typically for the vertical asymptote, we're looking for where the denominator equals 0. But for non-rational functions, I guess a rational function is one where the numbers are irrational, right? To find vertical asymptotes of rational functions at any point. Oh, I guess, okay, there's no trick to it. We just we identify points where the function is undefined or discontinuous. Okay. That's true. That's how we find vertical asymptotes. What are the three conditions for a function to be continuous at point? So at point C, f of C has to exist. The limit of C has to exist, and f of C and the limit of C have to equal each other. We use algebraic manipulation to pull out, or I guess to get to a different different equivalent form of the function that would have a limit, or like it doesn't resolve to undefined, something like that. The leading coefficient is the coefficient in a polynomial, or an expression maybe, that has the highest degree of a polynomial. Okay. The tangent secant Pythagorean identity is tangent squared theta plus 1 equals secant squared theta. We determine a limit exists within a function for how do we determine? Okay, so the first step would be to just substitute the value for it and see if it evaluates. If we're dealing with indeterminate forms, we can use L'Hopital's rule. And then additionally, let's see. We can also take the limit. Okay, those two things. Okay, I'm noticing something. I recall last time that like I had an intuition for what something would evaluate to, and then but I wasn't able to like prove it. And so okay, when you have like trigonometric forms, or I guess when you have components of the function that have when you have components of the function that are bounded, you could also use the squeeze theorem to evaluate a limit. You could also use algebraic manipulation to determine where the limit's at. Yeah. Okay, check if direct substitution yields a finite value. If indeterminate, evaluate if indeterminate, evaluate the limit from the left and right. If the left hand equals the right hand limit, the limit exists. If the form of the function is indeterminate. Okay, I don't think this is correct because we're asking for indeterminate. So maybe, okay. We'll see how this goes. Okay, evaluate the function, check one-sided limits. Then we go indeterminate. Okay, notice that we can use, so we can simplify the function, we can use L'Hopital's rule. Okay, I think I need to review this one more because I don't feel like my Yeah, I think I'd like to do more work on finding limits. Like legit practice. I know, surprising. He's actually practicing the math that he's learning. Okay. Okay. Yeah, because I just don't feel like I have the feeling for it quite yet. And so, I will. Okay, so I'm just going to send this one to be 18 days out. The derivative of cosine of x is sine of x. Okay, I'm going to have to do some work on those as well, because I just consistently get those wrong. Work on derivative and antiderivative forms for common trigonometric functions. Okay, we'll just put that one out 2 days. That's cosine. Derivative of sine of x is cosine. The cotangent reciprocal identity is sine over cosine. Or the reciprocal identity, not the quotient one. Okay, antiderivative of cosine of that's sine. How do you find the vertical asymptotes for non-rational functions? You just look for areas in the function where it's undefined. And when it approaches infinity. Okay, that's actually a really important point. When we take the limit from one side, we should get negative infinity. And we take the limit from the other side, we should get positive infinity. I'm going to send that one through one more time. So this would be 1 over tangent theta. This is where you look for parts of the function where it or values that evaluate to undefined. And then you also take the limit from the left side and the right side at the given value. And if one of them equals positive and the other equals negative infinity, then you should be in a good spot for saying it is indeed a vertical asymptote. Nice. Okay. So one thing. Oh, don't look at me for shame. I don't have my. I didn't do it. I know. One thing that was really good about today's study is that I was quite surprised with how well I had the trigonometric function stuff down. I didn't think it would be as good as it was today. So I'm excited about that. That they've sort of locked in. I thought I was going to have to do more work on that. I still have to do work on the derivative and antiderivative forms for the common trigonometric functions, but like at present, I'm actually quite pleased with that. I do think that after I complete this, actually tomorrow, we should be able to start making more, progress more quickly. Okay. Yeah, and actually, the number one thing that enabled me to have I think the number one thing that enabled me to have the understanding was doing the little deep dive I did on the unit circle. Because now that I know that cosine is x and sine is y, then I can understand that for the unit circle, and I guess this is the case generally. Well, I guess that doesn't give me... yeah, I guess then I'll know that the like sine and cosine are bounded from 0 to 1. And then tangent, because they're the interaction between cosine and sine, are inherently not bounded to that. Because if if my denominator is small, then the number gets really big. There is a relationship between cosine and sine that like determines their interaction. But I think, yeah, I think it's reasonable that you'd have, like, yeah. I think we're right on with that tangent there. Okay, so next, so the domain and range. Okay. Okay. Okay, I'm feeling actually decently good. I still have to do Riemann sums. I feel like this will be done in less than a day. And then I feel like this one will probably be done... Like, I feel like this one will take less than an hour. Or, sorry. 3 will take less... Well, will take at most an hour for me to learn and do all that stuff. I think 4 will take at most an hour. And then... I have to learn about Riemann sums. Okay, more Riemann sums, and then I have this really nasty one. It's gonna be a bit of a doozy. But actually, I think it might be sort of okay. Yeah, it'll be rough to evaluate, but I mean, yeah, I think it'll mostly be rough. Anyway, so that's to say, even though I'm only on number 2, there are only 6 questions, and obviously all the little sub points. So, yeah, I'm hoping to finish this one. I think I've said this a few times before, but I'm hoping to finish this one relatively quickly because I want to get on to statistics. I'm like so hyped for statistics, and so I've just been like just thinking about it, you know. I'm really excited to dive into like statistics and probability. I think it'd be way fun, and so I'm excited. Yeah, and then I think just in the general case that I'll be able to get more use out of statistics and probability than I would with an equivalent like depth of understanding between calculus and statistics and probability. So yeah, I think that is the case. And I'm also excited for the calculus cards to enter my main deck. That'll be exciting. Yeah, a whole lot of exciting stuff. And then I think I haven't decided what I'm gonna do for this channel. I think I'm going to I might just have the lives live on a different channel, because for the main content I'm doing, or I will be doing, someone who watches the main content may watch the lives, but I don't think someone who watches the main content is likely to watch the lives. And so I probably will just what is it, cordon off. Yeah. To cordon off. That's probably not the best word for it. I'll probably just use a separate channel to house all the lives, and then to have a main channel that has all the content, so as to not wreck the main channel with the lives from the secondary channel. So I actually might start streaming on a different channel. But yeah, I guess we'll see how that goes. Well, I think I'm going to end for today, and we'll catch you guys tomorrow.